by a pinch of oxygen in the air. And over there, a lot of hydrogen. A little bit of phosphorus here to stain the plants. And here, oh, it's the camera. Hi, viewers. Welcome to Jagan's channel. And today, with me, Jagannath, we will be exploring chemistry. What chemistry? Atoms, isotopes, polyatomic ions, isotopes again, and electron configuration, and so much more topics we're going to talk about today. So, why waste time? Let's get going. Now, before we need to know about atoms, elements, molecules, compounds, electron configuration, we need to know about matter. What is matter? Matter is anything with mass and volume. And anything with mass and volume is matter. Matter is divided into two portions in chemistry: pure substances and mixtures. Pure substances are stuff that cannot be broken down by physical means, like knives, spoons, filters. They can only be broken down by chemical means. And on the other ladder, mixtures can be broken down by physical means. Now, pure substances are divided into two categories again: elements and compounds. Now, elements are a big thing in chemistry. What are they? They are atoms, basically, with properties such as luster and color and malleability, and they have three subatomic particles atoms have: protons, neutrons, electrons. That's what elements are. Compounds, on the other hand, are an attached number of elements together. Some can form molecules, which are the same element, and a lot of them form compounds. Now, the difference between these two is elements cannot be broken down by physical means or chemical means either. But these compounds, they can be broken down by chemical means, but not physical means. That's why they're still pure substances. Now, mixtures, they are divided into homogeneous and heterogeneous. Now, homogeneous is when the two substances, otherwise called the solvent and the solute, they get dissolved together into a solution. Homogeneous mixtures are called solutions too. And they mix together so well that you can't define the ingredients. For example, salt water in the ocean. You can only see water, but in that there's sodium chloride, aka salt. So these ingredients are so well mixed that you can't see the difference between them. Now, heterogeneous mixtures, on the other hand, are, for example, water and oil. You can see them both. So you can define the characteristics between both of them. You can see their differences, and they're separated. Homogeneous mixtures are like water and dirt. Before we move on, I'd like to go to a chart to define these and not get mixed up between pure substances and mixtures and solutions and elements. Whiteboard, you're on.
Hello. Do you remember me? I'm Mr. Whiteboard, the guy from the physics video. If you haven't watched Motion, then watch it. Now, he told me to make a chart of the matter properties, and so I did. Mr. Whiteboard always keeps his promises. Extra smile. Now, while I'm doing my smile, we will discuss. So here, matter, as he said, is divided into pure substances and mixtures. Right? Right. Pure substances, they cannot be divided by physical properties, and mixtures can. Elements and compounds are the results of pure substances. Elements cannot be divided by, chemical properties or physical properties. But compounds can be divided by chemical properties, but not physical properties. Now, homogeneous mixtures. They are mixed up. They are solutions like salt and water. You can't really see the salt in water unless you evaporate it. Yes. And heterogeneous is, to be frank, something you can't see, like water and oil. Never get old. No, I'm afraid that's it for mixtures, but I will come back. Imagine the new movie, Return of the White. Okay, fine. I'm going back to you, Jagan.
Now, let's dive deeper into the atoms. So, what are atoms? Atoms are the smallest thing in the universe, and they make up the entire universe. They make up the sun, they make up the clouds, they make up the plants, they make up the animals, they make up humans. They make up even non-living things like rocks, they make up water, they make up that airplane over there. Or is that a helicopter? Anyway, everything they make it up. Now, atoms, they have even smaller particles called subatomic particles. And what are they? Protons, neutrons, and electrons. Protons have a mass, an atomic mass of about 1. Neutrons also have 1. A and U. Electrons have less than 1, like 0.9, a decimal number. People still haven't figured it out yet. Protons have a positive charge, obvious. Neutrons have neutral, and electrons have negative charge, obvious. As you know, there is a nucleus composed of the neutrons and the protons in the center of the atom. And apart from the nucleus, there is this big electron cloud where electrons orbit. And in there are shells, also called orbitals, in which the electrons orbit on. The electrons orbit around the nucleus. Then we have the periodic table. We're diving into variance here. Whiteboard, we need your help.
See? I've returned. And this time we're talking about atoms, if Jagan is not mistaken. Now, he told me that like this. Now, the nucleus is made up of the protons and neutrons, while the electrons are in the electron circle. Right? Right. So, no. Now, here we have. Let's draw hydrogen. Hydrogen has only 1 proton and 1 electron and no neutrons. Very ideal for the first element of the periodic table. Now, we have hydrogen. And now I'm going to draw how it will look on the periodic table. The atomic number is the number of protons and the number of electrons if there is no charge. The atomic number is always written over here. And the atomic mass is right over here. And it helps with identifying neutrons. So let's say if there now the protons plus neutrons equal to atomic mass. So what will the neutron number be? A atomic mass minus proton number equals the number of neutrons. Now, we have that written down, and then you know the name of the element and the chemical symbol which is used in formulas.
Now this is very important. There are 2 types of electrons. Valence electrons. They are the electrons that are on the outer shell of the atom. core electrons are the ones beside the valence electrons, which are in the inner shells of the atom. Now, valence electrons have a lot to do with chemistry, like chemical bonding and electron configuration and recognizing periods and groups on the periodic table whatsoever.
And now we're going to be talking about the octet rule. Okay, so how do we know? Okay, if this is the nucleus and this is the electrons and this thing is the shells or orbitals, right? So how do we know how many electrons to put on each shell? Well, the answer is there is this rule, the formula, 2n squared. So, n, what does it stand for? N stands for the shell number. Now, what do I mean by that? So, the rule is we have to put 2 electrons on the first shell and 8 electrons on the second shell. Right? Yes. So how do we know that? So we replace the shell number with 1 if we're talking about the first shell. 1. Then it becomes 1 squared is 1 only, and 2 times 1 is 2. But, oh no! What if we had this second shell? We replace n with 2. 2 squared is 4, 4 times 2 is 8. What about the third shell? 3 squared is 9 times 2 is 18. Right? So that's the rule. Now we're gonna go to the periodic table. I got an image of the periodic table. So let's practice. Now, I've been given that sodium is right over here at 11. So its atomic number is 11. So what does that mean? It has 11 protons and 11 electrons if there is no charge. And now to find the number of neutrons. The atomic mass shown on the bottom is about 23. So how much will it be? 12 neutrons. Yes, I'm so clever. And you'll be clever too. So now its symbol is Na and the name is sodium. Now we have shells. How do we determine the number of shells in an element without having to count? Well, here's the answer. So the groups means horizontal lines. So there are, there are 1, 2, 3, 4, 5, 6, 7 of these groups. And they determine how many of these they can be. What do I mean by that? Let's see. For example, let's go with beryllium, number 4. Now we have here, what do we have? We have beryllium, and it has 4 protons and 4 electrons and 5 neutrons. And how do we know how many shells it has? This is period 1, this is period 2, so it must have 2 shells. Let's double check. So it has 4, right? So 2 should be on the first and 2 should be on the second, so it has 2 shells. Let's try with a bigger example. Let's try nitrogen. Nitrogen let's try iron. Iron is a transition metal in the yellow one, which is called transition, and it has 26 electrons and protons, and 55 is the atomic base. So 55 minus 26 29. Interesting. I'm afraid this is going to get a little bumpy. Now, we have here, how much shells are there in iron? I'm giving you 10 seconds, and here's a hint. Horizontal line. I'll give you just a hint. Yes. Time's up. Now we have here. This is the fourth. Why? This is the fourth row. Right? So there must be 4 shells. Let's double check. 1, 2, 2, 10, and then 3. There should be 18. Ah, yes. Yes, we have it. There are 4 shells. Now, ions. They are atoms that have lost or gained an electron by some chemical bonding process. Now, ions are 2 types. Cations are ions that have lost an electron because then they have a positive charge. Anions are ions that have gained an electron because now they have a negative charge. Now, we are talking about valence electrons, right? Right. So, valence electrons are the ones that are outside, the outer shell of the atom. And so, how are we going to determine the valence electron of carbon? How much valence electrons are there in carbon? Well, it's actually quite simple. So, as you can see here, the periods of the periodic table are the columns. The groups are the horizontal lines, but the periods are the columns. And it says right here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. So how do we figure out? So let's ignore these numbers and write that this is 1, 2, and then it starts from here. These transition metals are hard to figure out the valence electrons because transition metals have several properties that make the valence electrons switch from 1 to 2 to 3. That's why they're transitional. That's why they're called transitional metals. So here, oh no. Yeah, so now 1, 2, we don't need to worry about these. And instead of 13, we put 3, 4, 5, 6, 7, and 8. So, where were we? We were at nitrogen. Nitrogen, how many valence electrons are there? Well, as you can see from this exquisite explanation, there are 5 valence electrons because the columns determine how many valence electrons the element has. So even if you go to, nitrogen, it has 5 valence electrons. Arsenic, it also has 5. Antimony also has 5. Bismuth also has 5. And moscovium also has 5. So all of the elements in one column have the same number of valence electrons. So now one quiz, quickly. Okay, I'm gonna actually keep these. What is the valence electrons, the number of valence electrons in organoson? I'm giving you 10 seconds on the clock. 5. Time is up. So, if you got 8 valence electrons, you are correct. Why? Because 8, this is the 8th column, right? And all of the elements in this column have 8 valence electrons. Alright? So let's review. Groups are the rows of the periodic table, and they determine how many shells the atom has. So for example, if we were to take krypton right over here, the noble gas 36, we could say that 1, 2, 3, 4, it has 4 shells and 8 valence electrons, because this is in the column number 8. Alright? Well, except for helium, that's an exception. Helium is the only exception for the valence electron period thing, because it can't have 8 valence electrons, so helium is the only exception.
Now, our next topic is chemical bonds. And with this topic, it's a little hard for me to explain, so our whiteboard fellow is going to help us.
Yes, yeah. So, chemical bond is a process where 2 or more atoms get attracted to each other by the valence electrons. So, what do we know? So, let's say sodium chloride is salt, table salt. So, we have sodium and chlorine in this one. And in this one, valence electrons is the most important part. We have 1 valence electron in sodium and 7 valence electrons in chlorine. So let's imagine sodium, which has 1 valence electron, and chlorine, which has 7. And now we have the octet rule. The octet rule states that each atom should have 8 electrons. So, here, if sodium gives one of its electrons to chlorine, chlorine will have 8 electrons. And then sodium will be more, once they bond, the greater and lesser forces when they bond, it will be like sharing chlorine. So it will be like here chlorine has 8, but sodium also has to have 8. Otherwise it won't be good. Octet rule will disappear. But chlorine can give away its 8. How? In chemistry, when one element has an 8 and it's attached to the other, both elements are considered to have the 8. Right? Right. So, now they are both bonded. This is called an ionic bond. An ionic bond is when greater forces and lesser forces of electrons are attracted to each other by giving away and getting the electrons. Right? So then we have hydrogen. Hydrogen disobeys the octet rule because it's the king of all elements, even though it has only 1 electron, but it is the first element, so it has to disobey the octet rule. Here's how. So here's hydrogen, and if another hydrogen comes, then hydrogen both have 1 valence electron. It's their only electron for that matter. Then they can both connect to each other, and once they connected, like the equality law of chemistry, they both have 2. So another rule for hydrogen states that hydrogen is satisfied with 2 electrons, not 8, 2. Let's move on to the next one, covalent bonding. Now, covalent bonding means they are sharing the electrons. And metallic bonding means, what does it mean? Metallic bonding is a little complicated. It is the electrostatic attraction of metal ions in lattice structure. Lattice means crystal structure. Something like this. 1 minute. So, yes, it's a crystal-like structure. So it's the flow of electricity in this lattice structure that attracts the metal bonds and is the reason why metals are good conductors of heat and electricity. One more way you can really be good at identifying bonding is by drawing the Lewis diagram way. How? What is the Lewis diagram? It is a perfect way. Now, this is a way to document bonding. Let's take our good old example, sodium and chlorine. How much does sodium have? 1 valence electron. How many valence electrons does chlorine have? 7. So you get to draw the dots wherever you want, as long as there are only 2 dots on each side. 1 is also there. 1 is acceptable. 1 or 2 dots. No more than 2. Alright? Right. So now we are blending it. Right? So when we do the covalent bond, let's do covalent bond. I didn't do an example for a covalent bond. Hydrogen and hydrogen. Remember, this has nothing to do with the octet law. So when we share these 2 electrons, it's a good way of documenting that the hydrogens have shared their electrons and now they both have 2. And we put it like this, a column, which can also become a line. So this means it's a single bond and it has 2 electrons in it. But then there is 4 electrons, or a double line. And here's how we do it. Let's say oxygen. Great. Oxygen has 6 valence electrons. So when they are moving and then they bond, they share 2 of their electrons with the other, and so it becomes a double line, 4 electrons. So that means each gets 4 electrons and both of them are happy because 2 plus 4, this is 4, and this one's happy because it has 8. This one is 4, this one's 4, so that one's happy too because it has 8. But there is a few circumstances that there is a triple line or 6 electrons. A good example of that is nitrogen. Nitrogen has how many electrons? Can anybody guess? Valence. Nitrogen has 5 valence electrons. So we'll draw it as this. So here. Now we donate 3 of their electrons. And then we put a triple line because then we have 6. And then both of them have 6. So 2 plus 6 is 8. 2 plus 6 is 8. And they're both happy. So that is an example of a covalent bond with a Lewis diagram. Now I'll teach how to draw a molecule with the Lewis diagram. So first, let's say we're drawing. How about HO2? No. Good old water. So the first step is that we identify all the valence electrons. So hydrogen has 1 valence electron, right? And then oxygen has 6 valence electrons. But I wrote wrong. It's H2O, not HO2. That means there are 2 hydrogens. So that means 1 plus 1 is 2. So H2, which means 2 hydrogens, they have 2 valence electrons. So 2 plus 6 is 8. 8 valence electrons altogether. Then we identify the central element, which is oxygen. Then we do the single bonds with what? Hydrogen. And now there are 4 electrons left. And now the lone pairs, right? Lone pairs mean the 2 electrons. 2 sets of electrons. And now that's it. We created HO2, H2O in molecule form. Let's try another one. How about SO3? Do you think? Sulfur has 6 valence electrons and all the 3 oxygens together have 18. So 18 plus 6 is 24 valence electrons. That's a lot. Then we identify the main element, which is sulfur. Then the single bonds to all the 3 elements of oxygen. I'm just gonna keep it over here. And then we identify the lone pairs. So how do we do it? So we already donated 6. So now there's only 18. And 18 divided by 3 is 6. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6. Now we double check if everyone is happy. So this oxygen has a 2 and a 6, so it's happy. This oxygen has a 2 and a 6, so it's happy. And this oxygen has a 2 and a 6, so it's happy. But the sulfur is not happy. Why? Because it only has 6 valence electrons. And we need the octet rule, which is 8. So here's what we can do. One oxygen atom, whatever one you want, can donate its 2 electrons to sulfur, being a kind gentleman. And then it will form a double line. So sulfur will have 8, because 4 plus 2 is 4 plus 4 is 8. And then this oxygen will also have 8, because 4 plus 4 is 8. So everyone is happy, and we made sulfur with 3 oxygens, the molecule. And that, my friend, is how you draw Lewis diagrams and connect them with a bowling ball. Very nice strategy.
Now we have electron configuration. Electron configuration is a way to figure out how many valence electrons are there in an element. So this, my fellow whiteboard, is going to explain.
So if I was speaking, Jagan was just trying to say about electron configuration. Boy, he's passing everything to me today these days. Now, when we're doing electron configuration, it is the easy method of identifying all the electrons with the valence electron. So we need to memorize these. When we're drawing an atom, there are several ways of drawing it. There are 4 shells: S, D, P, F. So the S, D, P, F way is one way, SDPF, and so on. So SDPF, 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 it keeps repeating between shells. So shell 1 is S, shell 2 is D, shell 3 is P, shell 4 is F. So here we have electron configuration with, so these two are part of the 1s. Okay, I'm just gonna write it on top of the 1s scheme. 1s. So the S, the first S sheet, and then we have 2s, and then here 2p, all of this, and then 3s, 3p, all of this, 4s, and then I'm afraid it starts from 3d, from all here, and then 4p. It keeps going on. 5s, 4d, 5p. Then 6s, 5d, when we are going to the lanthanides and the actinides, so 6p. I'm just gonna finish drawing this. 7s, 6d, 7p. When we're going to the lanthanides and actinides, we count lanthanium and actinium as one of these. Okay, so this becomes 4f and 5f. So you get it, the SDPF. Now let's figure out the electron configuration of neon. Neon is over here. This is our destination. Neon. Okay, so we write 1s2. So because it has two 1s's, it completed two 1s's. And then space 2. Okay, this is a little big. 1s2. Then 2s2, because both of the 2s's are completed. Then 2p, 1, 2, 3, 4, 5, 6. 2p6. That is the electron configuration for neon. Let's try a different element now. One a little farther. Let's try krypton. We can actually put the nearest noble gas in parentheses besides krypton itself. So the one above it, argon. Then we here have 3d, 4s. Wait, get it? 3d what? We have all of them, so it's 3d10, and then 4s2 and 4p6, because krypton is the sixth one in 4p. Now let's try a lanthanide or actinide. Here we have the SDPF. So we can start from the nearest noble gas. Let's start with, let's do a tough one. Okay, I can't really see. Einsteinium. Einsteinium is a good one. Einsteinium is 99. So, let's go. Lanthanide, this is part of the actinides. So we select radon as our nearest noble gas. Then we do the actinides. So this is 5F. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So Einsteinium is the 11th actinide, but we don't count actinium. So it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10th. So it will be 5F10. Then only 6D1, because this is still there. This is part of the actinide. So we do 61 and then 7s2. Sometimes for the transition metals and the actinides and lanthanides, it can get really hard and tough. But when you do these problems every day or every week, and when you practice them, you will get used to it very much. So that is the end of our electron configuration part.
Lastly, our last topic for today is the polyatomic ion. This is very, very, very important. The definition of a polyatomic ion term is a group of atoms that has a charge. What do I mean by that? Nitrogen, let's just take that as an example. Nitrogen is a singular atom, just one. And it gains or loses an electron when connected by a chemical bond chemical bonds. So when we say that, it means that it's getting a positive charge or negative charge. That means it loses an electron and it gains an electron. But what I mean by polyatomic ions is not just one singular atom having a singular charge, a group of atoms together, it gains and loses electrons and thus has a positive or negative charge. For example, nitrate. Nitrate is, the chemical formula is NO3 and the charge is 2 minus. Now what do I mean by that? It probably lost an electron or 2, or it gained an electron or 2. Now that nitrogen and the 3 oxygens are there together and their electrons are cooperating to be together and emit charges at the same time. You know what I mean? Yeah.
Here are the 9 main polyatomic ions you need to know. Number 1, nitrate. I mentioned in the video, Jagan mentioned in the video. So nitrate is, the chemical formula is N oxygen 3 minus. So here, it means in charge. So N stands for nitrogen and oxygen 3, there are 3 oxygens. Now, second one. Carbonate, which means CO3 2 minus. And the next one, sulfate, SO4 2 minus 4. Phosphate, which is the chemical formula P043 minus. Then chlorate, which is Cl, that looks like an L, Cl oxygen 3 1 minus. 6, which is ammonium, NH4 plus. 7, hydroxide, 0. Oh, oxygen, hydrogen minus. I'm gonna have to erase this also. Nitrate, carbonate, sulfate, phosphate, chlorate, ammonium hydroxide. We'll just erase. Now, the remaining two, acetate, which is C2H3O2, aka carbon 2, hydrogen 3, oxygen 2, and finally cyanide, which is Cn minus. Alright? Right. Now we're going to focus on how to name a polyatomic ion. So first, important thing number 1. The metal is always followed by the polyatomic ion, and everything's in lowercase. Important thing number 2 is always balance out the charges when finding the formula to the periodic table. So I'm going to be writing out the charges. Plus 1, plus 2, then we ignore these. Plus 3, minus 2, minus 1. Wait a minute, that's not how it's supposed to go. Minus 2, minus 1, and 0. Right? Right. So first, let's go to example 1. Magnesium carbonate into the chemical formula. So, first we have to find out where is magnesium in the periodic table and what its charge. So, magnesium, and since it's below the 2 column, 2. And then carbonate, if we remember well, is CO3 minus 2. So 2 minus 2 is 0, so it will balance out the charges. So our remaining is MgCO3. Alright? Now our next one. Now our next one is form this chemical formula into words. So lithium stands for Li, and it's under the charge 1 plus 1 plus 1. So lithium 1, and then C2H3O2 stands for the polyatomic ion acetate. So it will be lithium, if we're going to have to spell it out, acetate. Remember, everything's in lowercase. And now, our next example. Now this time with different charges. Now convert lowercase. Aluminum sulfate into the chemical formula. So let's go. Aluminum is under which one? Aluminum is under plus 3. So aluminum is Al3 plus. Then sulfate is the polyatomic ion S042 minus. So how are we going to do this? This transforms to, we switch the charges. So this transforms to aluminum 2 parentheses S04 outside 3. It makes sense, doesn't it? Very nice. Now our next one. There. our next one, convert this one into words. So remember, it's in lowercase. Calcium is the metal. Calcium. And if we remember, HO stands for hydroxide. Yay! Very nice. Now our last example for today is convert ammonium sulfate into the chemical formula. So ammonium, if we remember properly, is NH4+. And sulfate is SO2-. So if we convert it well, we have to switch up the phrases. So NH4 in parentheses 2 times SO4. That's simple. So that is our last example, and the last time you'll be seeing me in this video. I'm off to chemistry land. They're making a new amusement park, and only for whiteboards. Goodbye now. Goodbye. My singing.
Thank you for watching, and I hope you had a happy learning time learning about atoms and polyatomic ions. Please subscribe. That's the end of the video. Now, I'm going to continue counting my atoms. There's a little bit of granite in the middle, and there's a phosphorus, another phosphorus, some oxygen in the earth, some basalt, and there, and oh, whoa!